In this video we're going to be looking at transformers, and here's an example from my microwave oven. It consists of two coils, a primary and a secondary, and these are surrounded by a very substantial piece of iron. The iron actually goes through the middle of these two cores, and this is something what we call an E-core. It forms an E-shaped with an end plate on it. The primary is much thicker wire because it carries more current, and the secondary has a lot more windings on it, and we'll see why later. But basically this transformer has 240 volts in and around 2000 volts out. It's what we call a step-up transformer. So what we'll do is have a look at how does this thing work. A transformer relies on two key physics principles: electromagnetism and electromagnetic induction. Electromagnetism is when an electrical current generates a magnetic field. Electromagnetic induction is where a magnetic field causes an electrical current to flow. As you can see, one is just the reverse of the other. The basic transformer construction consists of a primary coil magnetically linked via an iron core to a secondary coil. The primary coil generates a magnetic field, and the secondary coil converts that magnetic field back into a flow of current or a voltage. So if we look at what goes on in a wire when we pass a current through it. When we pass a current through a wire, the red arrows representing the increase in current flow, a magnetic field is formed. To get a stronger magnetic field, we get more current to flow through the wire. Alternatively, what we can do is use two wires. Doubling the wires effectively doubles the current flow past a certain point, and therefore it doubles the magnetic field strength. We can use this in a transformer to make some very strong magnetic fields by using a coil. We can use this principle of multiple wires to greatly increase the strength of an electromagnet. By looping a wire into a coil, the same current carrying conductor passes the same point repeatedly. The magnetic field from each wire effectively adds together and makes for a very strong magnet. So if we look at what goes on in a transformer core, if we start with our coil of wire, if we now take a cross section through the coil and only consider the wires going into and out of the screen. By convention, we represent objects going into and out of the page using dots and crosses. And imagine an arrow being fired from a bow. If you can see the cross of the feathers of an arrow, it's travelling away from you. If you can see the point of the arrow, it's heading towards you. We can now add the magnetic field of each conductor as we have seen previously. The magnetic fields actually add together, creating one larger magnetic field, and we can represent this with field lines showing the combined or the resultant magnetic field. What we can then do is wrap this coil around an iron core instead, or a loop of iron. Now when we do this, because magnetism passes through iron much better than it does through air, we actually find that the magnetic field is constrained within the iron core. It permeates the iron core. Permeates just means travels through, basically. Iron can be several thousand times better at conducting a magnetic field than air. So if we now look at the primary side of the transformer, we can see how we generate this magnetic field which passes through the secondary coil. And what we'll now look at is induction in the secondary coil. The principle of induction involves moving a magnetic field past a conductor. In this view, as we move the magnet through the wire, some electrons move. We move the magnet the other way, and the electrons move in the opposite direction. The key thing is if I move the magnet faster, more electrons move. So the faster I move the magnet, the greater the current flow. But key to this is that it's a moving magnetic field that causes the electrons to move. In other words, a changing magnetic field generates a current. So let's have a look at that inside the transformer. First, looking at the primary side of the coil, the red arrows represent the magnitude of the current, so bigger arrows, bigger current. I increase the voltage, the current increases, and I get a growing magnetic field. But once the current is the same, the magnetic field is static, it stays the same. So let's look at that again. Increasing voltage, increasing current, changing magnetic field, Voltage stays the same, current stays the same, magnetic field stays the same. The key thing is, the voltage is only induced in the secondary coil when the magnetic field is changing. So as long as the magnetic field is changing, we've got a voltage in the secondary coil. But once the magnetic field stays the same, there's no voltage induced. So just watch that again. Changing magnetic field, we have a voltage in the secondary, but when there's no change in magnetic field, we have no voltage. So what we actually need is an input voltage that changes constantly. And we can do this using a sine wave. As you can see, the sine wave constantly changes voltage, which constantly causes a change in magnetic field, which means we're always going to have a voltage induced on the secondary. So we now have seen how a voltage and a current flow can be induced in the secondary. The induced voltage depends on the strength of the magnetic field and the number of turns on the secondary coil. More turns on the secondary will generate a larger voltage. The strength of the magnetic field, though, depends upon the number of turns on the primary. So the voltage output of a transformer depends on the relationship between the number of turns on the primary and the number of turns on the secondary. So let's now have a look at that relationship. This is the transformer formula, and it's one that you need to know. It simply tells us that if we take the ratio of the voltages, secondary divided by primary, it's the same as the ratio of the turns, secondary divided by primary. Easiest way is to go through some examples. If we take 10 turns on the primary and 10 turns on the secondary, we look at the ratio, secondary divided by primary, and it's 1. 10 divided by 10 is 1. If we put that into our formula, and then rearrange the formula, what we know is that the output voltage on the secondary is 1 times the voltage on the primary, or that actually both voltages are equal. So equal number of turns, equal voltages. 240 volts in would give us 240 volts out. 10 volts in would give us 10 volts out. If we look at a different example where we have 10 turns and 5 turns, we now have less turns on the secondary. If we take the ratio of that, 5 divided by 10 is 0.5. We put that into our formula, rearrange it, and this tells us that the voltage on the secondary, the output, is half of the voltage on the primary. In other words, the voltage has stepped down. It's a step down transformer. We have half the turns on the secondary, so we have half the voltage on the secondary. You can probably guess what happens when it's the other way around. Again, work out the ratio, put it in our formula, rearrange the formula, and this now tells us that when we have twice as many turns on the secondary, we get twice the voltage on the secondary. This is called a step-up transformer. So in summary, voltage causes electrons to flow. Flow of electrons is a current. The current generates a magnetic field. By looping the wire, we can increase the strength of the magnetic field. The magnetic field passes easily through iron, and changing magnetic field induces a current in a conductor. Therefore, transformers have to use alternating currents. They will not work if you just connect them to a battery. The output voltage is equal to the ratio of the number of turns multiplied by the input voltage, or in other words, the ratio of the primary and secondary voltages is the same as the ratio of the primary and secondary coils.